Okay, let's start. So I see a lot of familiar faces here. So I'd like a show of hands for starters. Who here has any experience with RabbitMQ? Please raise your hands. Okay. So who here does not have any experience with RabbitMQ and would like to learn? Awesome. And how many of you have come here to see how much of an ass I will make out of myself? Okay, I'll try not to disappoint. So, let's start. Practical RabbitMQ. Let me introduce myself. My name is Srdjan Vranac. I run a small company called Code for Hire from Novi Sad. I'm from Novi Sad. The company is based in Hungary. We are a small team. We are developers, consultants. We write terrible code that performs exceptionally. We wrangle elephants and pythons on a daily basis. I'm obsessed with process automation. I'm interested in continuous integration and continuous delivery and deployment, clean code, testing, best practices, and of course, distributed systems. Before we begin, a word of warning. I'm partial to using images and slides, as I do believe that they can drive the message harder into your brain. And I also don't have a lot of code in my slides. And as we are speaking about distributed systems, the speaker or me may or may not exhibit race conditions with words, lagging thoughts, occasional set fault, or OM. This is not the result of stage fright or poor preparedness. This is a carefully choreographed act that you should not be tried at home. So, to kick it off, story time. Imagine you just made a shiny new application that scrapes information about products from different websites every 12 hours or so. It's a simple setup. You get the HTML from the URL, you look a few things in it, update the database, create a screenshot for auditing purposes, a cron job triggers the process, everything works well. The site is working, there are thousands or so products in the database and things are fine, until one day you get a call from the CTO and he says, you really did a good job. And we are going to use our primary product database on your system. The import process has started, and all 30 million products will be imported soon. So, things will start to fall apart. The cron job you have is not enough. You have 30 million products. You do a simple math, and you do the math that you discovered that for 12 hours to process 30 million products, you need to process 2.5 million products an hour. When you divide it in seconds, you get to the number of 695 products per second. Yeah. Or if you can spring for some 600 machines or processes or cron jobs, that's about 1.1 second per product, under, of course, optimal conditions. You might be able to get scraping done in the required time. Good luck trying to set up 600 or so cron jobs on a few machines that will be able to do this cleanly, or even better, to ask your client for 600 machines to set up for this task. Well, this is a good example for asynchronous processing. The asynchronous processing is, let me turn it around. So what is asynchronous processing? Let's say you have to access database records. You issue as many requests as you need in parallel, but you do not wait for the result. Eventually, the results will come back. Some kind of callback will be executed and triggered, and since everything is done asynchronously, nothing was blocked in execution, and that is always a good thing. The best way to build asynchronous systems would be to use messaging and queues. In essence, it is a simple system where a process issues a message. Somewhere there is another process that listens to the issued message, it understands, processes it in some way, and so on. With this, you can do a lot of things. In the same way, you would build a queue system where you queue some messages, and there is a worker process or a consumer process that asks for the first available message, does something with the information on the message, and so on and on. With this, we can build distributed systems. So what is a distributed system? Well, the simple definition is that a distributed system is a system where you can distribute processing of tasks to other workers. And I'm going to read this from the slide. By costly tasks, I mean anything ranging from heavy computation and CPU utilization to long-running processes. If we are talking in the context of web applications, basically anything that can't be done within a request is a candidate for distribution or background processing. A more realistic definition given by Leslie B. Lamport in '87, and this person is basically the granddaddy and the grand poobah of all distributed systems and related stuff, says that a distributed system is one in which the failure of a computer you didn't even know existed rendered your own computer unusable. And that is incredibly true. And this brings us to the subject of this workshop, which is RabbitMQ. So RabbitMQ is a open source message broker software, sometimes called message-oriented middleware. It implements the advanced message queuing protocol. The RabbitMQ server is written in Erlang programming language. It is built on the Open Telecom Platform Framework and it is enhanced for clustering and failover. Client libraries to interface with the broker are available for all the major programming languages. RabbitMQ consists of the Rabbit Exchange server itself, gateways for STAMP, HTTP, and MQTT protocols. There are MQ client libraries for Java, .NET, Erlang, PHP, and other languages. And it has a plugins as a platform for custom additions with some predefined collection of supported plugins like Shovel plugin that lets you move or copy messages from broker to broker, a federation plugin that enables you to efficiently share messages between brokers at the exchange level, and the management plugin, which enables you monitoring and control of brokers and clusters of brokers. And for the purpose of this workshop, we are going to take a look and use the management plugin later. So the next thing I would like to talk to you is the ingredients of a Rabbit stew. So first ingredient is an exchange. It is one of the basic concepts when working with RabbitMQ, and the easiest thing for you to remember is to think of it as a post office system. Basically, the exchanges will handle the routing of the messages that you send to their destinations and manage their delivery. Then you have the queues, which you can think about as your mailboxes, and the messages will be delivered to those mailboxes. Then you have the producer. This basically is any script of yours that will kick processes off and start the queuing. Basically, you will send a mail or an envelope into the post box. And then you have the consumer, which is basically your post box. He takes out the messages, processes them, and does it. So you can deal with one consumer, you can deal with many of them. The principle is still the same. He gets a message, does something with it, and moves along. And at the end, of course, you have the message, which consists of two parts. One is, let's call it an envelope. That is the binding key, the metadata, the priority, the time to live, and stuff like that. And then you have the payload itself, which can be either text or it can be a JSON. If you're sending things over as a plain text format, you can actually use it to send over the serialized objects and stuff like that. Unfortunately, you cannot mix serialization with the JSON payloads because that doesn't work for some reason. So now we come to the management plugin that I mentioned. To enable it from your console, you would type RabbitMQ plugins enable RabbitMQ management. That has already been done and provisioned in the virtual appliance. To access it, you need to open your browser and point it to localhost port 1500-672. And I would like to ask you to do it now to verify that it is working for everybody. You will be asked for user and password, and it is admin. Everybody managed to do that? Okay. Yeah. Yep. 15672, admin. What do you do?
Sudo, okay.
What? What's sudo? What do you need sudo? For the enable RabbitMQ plugin.
Yeah.
That's already been done. It's enabled.
Yeah.
We did it in provisioning.
Yeah, but
No, I just pointed an example of how you would like do it later. Damn it, today we will be not through this. And now we code. Okay, arrangement. We are going to now mirror the displays. Oh man. Oh, this is bad. Okay, can you see this? Can everybody see the screen? Okay, and things going on the screen, like the properties box and edit producer. Okay. So you open your console. Please go to Summer Camp, Workshops, RabbitMQ. Do git checkout. I'm sorry. Out master and git pull origin master to get the latest. Let me know if everybody managed to do that. And once you're done with that, please open PHP Storm and open the RabbitMQ project. Everybody managed to do that? Awesome. Okay, so we're gonna start by going through some basic concepts of RabbitMQ messaging architectures. First, we are going to look at PubSub, the different types of exchanges, Fanout, direct top exchange, acknowledging messages, remote procedure calls, and stuff like that. The idea is that I'm going to first show you a simulation of it and how you can build it. And then we are going to write code for it. And we are going to execute it and check it out in the RabbitMQ management plugin and stuff like that. So, PubSub. So this is the RabbitMQ simulator. Let me reload the page. Okay. So first I have the producer. Instead of this random name, I'm going to call it P for fun. Then we have the exchange. Again, great name, E. I'm guessing Tobias, if he's looking, he's trying not to hit me with anything. That's awesome. We have the queues. Let's call it Q. Actually, Q1 would be a great name. Q2. No. Producer, delete. Q3. Let's connect them. And we are going to start pumping messages into the queues and exchange and a rate 1% per second, or 1 message per second. As this is a basic PubSub, what you have here is your publisher will be sending messages to the exchange, and the exchange will automatically send them to any and all queues that have been connected to it and bound. If you need a real-world reference to this, this is basically how you would build a notification system for all mobile devices, where each mobile device would register itself to the system, and then it would pull and receive messages. So, because this is now queuing the messages in the queues, and basically messages are there, we're going to start adding the consumers. It doesn't really matter if it's going to be 1 or 10 or whatever, as long as one consumer is consuming one queue at a time. you can, and we probably will do something like if the Q1 is empty, the consumer will try to use Q2, but that is a completely different subject and something that may come up later. So this is C4. So there you go. This is basically your simulation of RabbitMQ and your first, shall we call, a design pattern for Rabbit, where you publish messages and all of your queues receive them and your consumers are able to process them. For this part of the exercise, what you need to focus is that the producer, is a PHP script that sends messages to the exchange, and consumers are, again, PHP scripts that are going to get those messages and do something with them. So, let's see. We got channel, that's fine. So we need a new, well, now this is fun. Oh, good. So we need a new file. We're gonna call it PHP file. We're gonna call it consumer. There we go. And in it we say we are going to use the PHP MQplib message and AMQP message. Next, we define the channel. Did I type it right? Yeah. Require dir dash channel PHP. Okay. So, in order to decrease the amount of things I need to type, I cheated a bit and created a channel PHP, which is basically just declares a new connection as a stream connection to your local host on a port 5672, and know that the difference between the management and your usual Rabbit port is basically 10,000. So just prefix 1, and that's it, with the username and password worker. In real world examples, you would change this to whatever you set or whatever your admin set. And this application is going to return the new channel. So we have this channel defined here, and we can do the type hinting, define it as var, and type is PHP MQplib channel AMQP channel, right? Okay, so we have that. So what we need to do now, excuse me, here we go. So what we need to do now, for example, is define the handler. So handler will take all the messages. Well, I'm fat fingering it more than usual from the queue, and basically it is a callable, or you can use function, whatever you want later, depending how you decide to develop this. MQP message, pass the channel that we got, and we print message body, and we add a new line, because why the hell not? So we defined our handler, and this is going to be passed to RabbitMQ library, and every time the message is received, this will be called and the message will be printed out. Expected semicolon, so I missed something lovely. Oh, right. Okay, so now we need to declare the queue. So we do the channel, and then queue. One of these days I'm going to type it from the first try. Declare test queue this is the name of the queue. Queue create. Okay. So we have, with this part, we will declare the test queue. So what we need to do is now to set up the consuming of the messages. So add the handler to consume the queue. For that, we use the basic consume command, channel, basic, consume. Really lovely. And now we come to the most suckiest part of a PHP AMQ plib, and that is that there is a crap load of booleans that you need to keep track of and remember. When I started working with RabbitMQ, on the second day I started writing my wrapper class around it, so I would actually have same names and same defaults, and I never looked back on it. When I was preparing the code for this, I just remembered how awful it is, so I apologize in advance. But you know, this is how you need to do it to get it, to learn it and then apply it to your needs better. So we declare the test queue. This is the name of the queue to consume. Then we need to provide the ID of the consumer. In our case, it's going to be worker. You can leave this empty, and PHP AMQ plib will generate some random string to use as your worker identification. Personally, I don't like that, because if you start scaling up and you need a lot of workers, you will have a tough time actually trying to track down. You will have the option to go through the Rabbit management and click on the worker and get to the IP, and then you need to detect which of the IP of the instance is it and go there. Or you can actually do a better solution and create a string that consists, for example, of the instance name, the worker, and the number, so you actually know where it is and you can just zero in on it with ease. So this is called a consumer tag. The identifier of the particular worker. Then we have, what do we need then? Then we need to say false, because we don't want, this false defines the no local value. If it's true, that means that we don't receive messages published by this consumer or publisher. If it's false, it means it's fair game. So I'm going to type that. Then we have another flag, true, that says no ACK. It means that the handler will not manually acknowledge the message reception and success if it's set to true, so no ACK. Then we have option to set the exclusive, which means that only this consumer may access the queue. In case of multiple consumers trying to access the exclusive queue, you will get some kind of an exception which you don't want. So we set it to false. And this is exclusive.
Two workers define the exclusive, which one is used?
Race condition, yes. That's the problem. So false. Exclusive, then what we have, yeah, false again. So we have next option we have is no wait. If you set it to true, that means that we don't wait for the server to respond. Non-blocking and not asynchronous, which means that the server we will just start consuming messages, not waiting for the server to tell us like if there is anything waiting for us. Under certain scenarios you can actually do this, but to be honest I never found a particular use for it. So this is a no wait. And then at the very end we pass in the handler. Okay. So we set up our basic consume command. And at the very end, we are going to set up a loop that will basically process all of the messages that have been queued on the server. So blocking loop, this is a blocking loop. Blocking loop. Let's see, while count channel callbacks, channel wait. Okay, again, wrong one. So what this does is basically ask the channel if there are callbacks or messages registered on queue, and wait if there are, because that means that the worker has something to consume and it waits for delivery. So this is basically your consumer PHP. So now we need to define our producer, which will... Is everybody managed? Yeah.
I have a question.
Serious one or? Okay, cool.
Whenever you add a consumer,
Yeah.
Does it consume the call queue, or it starts from the point of insertion?
No.
In the simulator, you...
Look, RabbitMQ queue is FIFO, okay? First in, first out. So that's the only thing that you know. Order of execution is not guaranteed, never. And we're going to cover that later. The thing is that basically if you have multiple consumers that are going to be operating under different conditions, depending on various factors like system load, like networking speed, database connections and stuff like that, some are going to be faster, some are going to be slower. So if you have queued messages, for example, with payloads 1, 2, 3, and 4, if you have one consumer, you will get it in mostly that order. If you have two consumers, you will get 1, 4, 3, 2, or something like that. Really, it depends. The moment that you have more than one consumer, you cannot have guaranteed order of execution. And in distributed systems, a guaranteed order of execution should never be an issue. It shouldn't matter. Okay. So where was I? Okay, so we're going to create the producer. And again, use PHP AMQP lib, message, AMQP message. So let's copy this part from, for example, this whole thing here. The channel can be copied over. Okay. Then we declare that the queue exists. So that's the same thing. Let's declare the exist queue. Okay. And now we can create a message that's so. So value can be anything, like we said, like text, JSON, or even binary data. If you're sending over binary data, it's supposed to be the text type. So let's do that. Message as new QP message, and the payload is hello.
Objects.
Excuse me?
Can you provide objects?
Yeah, serialize them and pass them over. Just make sure that you don't pass them over in a JSON payload, because that won't work. That specifically won't work, even that it should. Summer Camp 16 workshop. Okay, so we have the message now. And then we need to publish this message. We do that by using the basic publish. First parameter is message. So the message object. And the second parameter is the exchange name. We are going to ignore it for now. The third parameter is the name of the queue. Okay. There we go. And I need to put the semicolon at the end. Okay. So with this, we have a consumer and producer setup. Has everybody managed to do this? Okay. Awesome. What do you need? Yep. Here we go. Excuse me? It's committed already. Yeah. Just look in 001 PubSub. Oh, did you do the git pull?
I did, yeah. I'll catch that.
Yeah. Yeah. Thank you. Okay. Sure. Oh, well. Okay. Green on 1, green on 2. Good. Tmux. PHP producer, PHP. Yay, nothing broken. Awesome. So, open your console, go to the workshop RabbitMQ, and type phpproducer.php. And amazingly, nothing happens. Or has it? So, when you go into your Rabbit Management Console, and this is it, you will have an overview. And as you can see on the graph, a message has been received. So while we're here, let's do an overview of the RabbitMQ Management plugin. This is it. This is basically a web application, JavaScript, single page. It gives you overview of the messages. So you have the ready message, the unacted message, and the total, which is the total number of messages that you receive. You have the message rates, publish rate, confirm rate, publish in, publish out, how many messages were redelivered, which means that something happened with the consumer and the message was not acknowledged. So it was put back in the queue and waiting for either that consumer specifically or a new one, depending on the situation. You have global counts, you have your file descriptors, basically the overview and metrics for your system. Then you have the connections tab. At this point, it shows nothing, but as you connect consumers to your RabbitMQ instance, this is the place where you're going to see everything that is happening, and we're going to see that in a few moments. Same thing is with channels. The channels basically are virtual connections which allow RabbitMQ to handle thousands and millions of them at the same time without anything breaking. In the exchanges, you will see the exchanges we have defined. So we have the MQP Direct. These are basically the default exchanges. And if you remember, in the producer, we did not give the name of the exchange in the basic publish command. Just a sec. Here we go. So we see I left it blank. RabbitMQ is basically smart enough to say, oh, okay, there is no exchange name defined, so I'm going to use my default one. So your routing will still work. And finally, we come to the queues, which will show you all your defined queues. So this is basically the test queue. And this brings me to another important point. As you may remember, we had a code duplication in the consumer and producer. Basically, we declared the queue twice. This is done because you want to make certain that the moment you trigger any of your scripts, they will send out commands to RabbitMQ, and Rabbit will check if all of your setup exists. And if it exists, it will say fine. if something of the things that you need and define does not exist, it will be created. So if you need a new exchange, if it exists, it will just proceed. If it doesn't exist, the RabbitMQ will create it and then move along to queue. So this is basically a fail-safe system for yourself that you do not have to think about, like, what am I going to do if this is a new instance? Where was I? Okay, so you have the queue, and then, of course, you can click on the queue and get information about it. So this is the number of queued messages. You can change it from chart to current value to moving average, last minute, last 10 minutes, last hour, last 8 hours, last day. Do note that changing the range depending on the speed of your connection and the resources of your machine may take a while, because this is JavaScript after all. So be careful with it. You have your basic message rates, again, publish, confirm, publish in, out, redelivered, acknowledged, return. You have you have the details of your queue, whether it is auto-delete, the state of the queue, its idle, the number of consumers, the consumer utilization, and of course the overhead, like the number of messages, how much does it use, how much process memory it uses, and stuff like that. What is a good thing to say here is that, and note, is that RabbitMQ has persistence to disk by default. At some point, it will unload the messages that it has in memory onto the disk. So, in theory, if you set up your queues as durable, they will survive the RabbitMQ server going down and coming back up, because then they'll be loaded from the disk and it will continue. Also, this has a performance penalty, but in 99% of the cases, this is something you can live with, and you will notice it in normal execution. Next, you have like the consumers, you have the bindings of the queue. So as you can see, it says default exchange binding to this queue. You can add new bindings from exchange and routing keys. So basically, it is possible to have one queue bound to multiple exchanges. You can also publish the message. And this is the best part, at least for me, because when you start working with these things, sometimes you just need to figure out what the hell is going on. So you just say get message, and it will get you the first message in the queue. So it will say, this is the exchange, the routing key, whether it was redelivered, the properties of the message, and here you can see the payload of the queue, payload of the message, excuse me. So this is it. So with this, you are basically able to do testing of the output when you need to run it locally to see if everything is working properly. So here is the move. Of course, as you can see, this requires the shovel plugin, which has not been enabled. This is basically a move operation. So you say, I want to move all of the messages from queue A to queue B, and that's about it. Here we have, next we have the delete and purge. There is a slight difference here. The purge will basically empty the queue of all of the messages. Thing to note is that it will purge the queue from the messages that have not been prefetched. So this is a concept that I will talk about later, just keep this in mind. On the other hand, delete will basically delete the queue and all the messages without mercy, without prejudice. And here you have the runtime metrics, which can be interesting depending on your needs. Okay, so, the last part, sorry. And you have the admin tab where you can define the users. At this point we have the admin, the guest, and the worker. The guest user is enabled by default, and you can only use it if you access the RabbitMQ server locally, which means from this virtual appliance. If you try to access it from outside, you would not be able to get to this RabbitMQ management. By using admin and worker, yes, you can. You can also define virtual hosts, Basically, it will allow you to have multiple applications running on one RabbitMQ instance without having collisions and having to think about, like, do we rename the queue and stuff like that. So basically, it's like a separation of concerns. You can have two same applications running for two different clients, like for two different websites that have absolutely the same names and queues and exchanges, but they will be separate physically, and you will be able to filter it much faster. So, okay, here we go. So now we go back to the console and we execute the consumer, the moment of truth. And there you go. The message has been received. Queues, here we go. So we don't have any more messages. If we go to the test queue, we can see that it has been consumed because the queue has been emptied. And the best part is that if you go back to the producer and do a new one, you will just start getting them back. And there you go. So that is our first example. Did everybody manage to get this far? Okay. Let's then proceed to the next step. Okay. So the next thing we are going to talk about is the fanout. Let's reset this. So again, we have the producer, we have the exchange, we have the queue, now we set the type of queue exchange to fanout. There we go. And let's connect stuff. So for all intents and purposes, we can actually start publishing stuff. Okay. So this is what happens. So a fanout exchange means that if you have multiple queues bound to an exchange, and they have the same binding key or don't have the same routing key or don't have the routing key defined, they will receive every message that exchange gets. This is a rather good option. For example, if you need to ensure auditing for your messages and payloads, basically you would set up something like fanout, and one of the queues would basically be your primary consumers that actually process the message, while the other queue would have the consumers that would audit those messages and store them for later inspection and stuff like that. And this allows you that so you can actually set this up quickly and use it in the ways that you need. As far as the consumers are concerned, you just connect them to the queue and they will start consuming whatever is there, and that's it. So let's set this up. Switches. Oh, right here. So for fanout, we need to modify the consumer first. There will be no queue name when we declare the queue. So basically, we delete this. Oh, wrong one. So there we go. Queue declare. That has been removed. And because we removed the name, we are going to store it in variable queue. Again, not the greatest name, but it will use for our intents and purposes. So then we define the queue. Okay, name is Q0. What happened here? We declared a queue with no name, and again, the system in all its wisdom will then create a queue name for us, and it will be completely random, like AMQ _-- whatever. So basically, it will generate a queue name for us, which we can then use. So the next thing that we need to do is declare the exchange this time. Let's see if we can, done. Okay. So declare the exchange. We do that with channel, exchange declare. Test Fanout Exchange, just a great name. So, and we set the type to Fanout. Okay, let's see what we need. Okay, the things are now starting to get complicated, and because we are going to use multiple workers or consumers at this point, it would be good for them for each of them to have a unique ID. And for us, it will work to just get the process ID of the consumer. So we add get my PID. So basically what we will have now is worker underscore my PID. False, true, false, false, and the end handler. So basically that's it, I think. These are the changes required for the consumer. So we bound the queue to the exchange again. And the consumer now has a unique ID. On the producer front, let's see what we have to choose or do. So we need to remove the queue declare because we no longer want to publish to a queue. We publish to the exchange directly, who sends the correct queue, who sets the correct queue for us. And let's see, so we have the message, that's fine. Basic publish message, and for the exchange name we are going to use the test Fanout Exchange. So this is the exchange name, and we are going sorry, let's figure it. And we are going to comment out the test queue name. And I have an error. Great. Okay. So everybody got these changes in? Yep. Okay. Sure. Basically, the only change in this part is this worker underscore, and then you append get my PID. The queue name, that's queue. Or should it be? Did I make a mistake? Yeah, I did. Thank you. There we go. Okay, everybody got this? Okay. So, first we need to run the PHP consumer. Okay. So what this did is declared our test Fanout Exchange. And now when we click into it, we can see that the auto-delete is set to true. As soon as the last consumer has been disconnected from the RabbitMQ, the Fanout Exchange will auto-delete. Let's see about the queues, and here it is. Like I said, because we didn't provide a specific queue name, RabbitMQ generated a completely random queue name for us, amq.gen-whatever. And you can get and see whatever you need. But what is interesting now is that we can actually see the consumer that has been connected. So we have the consumer count of 1, and we can now drill down to get the information about the consumer. We see that the consumer tag here is worker4224, which is the process ID. And if we click on the channel, we are going to be taken to more information that we can then drill down to the connection level, actually see the throughput, so you can actually measure and monitor that if you need to. But to be honest, if you actually need to monitor this, then you're building a really heavy system and the ANVU. So we have the consumer setup, and let's do the producer. What did I do? Exchange point to Q. Okay, let's cheat a bit. Fanout producer. Actually, the consumer first. That's one. Producer. We want. Okay. Yep. And so let's see, I have the here we go. So now we publish messages and the consumer is getting them back, but we are dealing now with only one consumer, so this is kind of stupid. So what we can do is bring up a new one. PHP consumer, here's one more. And now when we publish the messages, they both start together. Or B space, there we go. So now as you can see, every consumer that is active will receive a copy of this message. In case you're stuck, you can use the folder 002 fanout and copy and paste from the consumer and producer to their respective files. You will just need to correct the path for the channel required. Yell if you need help or something. Does anybody needs to see the code or? Okay, can we move along? Does anybody need help? Okay, so now we are going to talk about the direct exchanges. So we've seen the Fanout, which is fine. And again, one producer, exchange, we set the type to direct, we have the queues, we have the consumers, sorry, and we start connecting stuff. Now, the biggest difference between so far is that our queues are now going to have binding keys. Binding keys are basically routes and routing, and if you remember the postcard example, basically that is your address. So if you send a postcard, you write an address, and the system, the post office, will make sure that it arrives to the proper queue or the mailbox. So we're going to set the binding key 1, change, and we're going to set the second one, excuse me, here we go, edit queue, here we go, binding key 2, change. Okay, the exchange is set to, right, okay, the exchange has been set to binding, where are you, to direct, fine. And let's see what happens when we send a message without no binding. The exchange will basically swallow it up and just like shrug and move along because it doesn't care. It has bigger fish to fry. But if we set the binding key 1 and send the message, it will get passed to its rightful destination. So with this, we can send messages to 1, and then we can connect, for example, another producer, or like create another producer that will start sending messages to the second queue. And the exchange will start routing this for us, and we will have no problems. And this is your basic RabbitMQ setup, where you have one exchange that can handle a lot of queues, and you're using the binding keys to route your messages to their desired destinations. Okay, let's see the code. So, channel is fine. I'm going to delete this, and let's see. Let's start with the direct from the consumer again. The handler is right. At this point we are going to queue declare. Again, no queue name, that's fine. We are going to change the name of the exchange to test direct exchange, and we are going to change the type to direct. So name of the exchange type. Okay, let's see what else we need. You got stuck?
No, my bad, keep crushing every single.
Damn, impressive. Okay, so now we're going to do something fun. Binding key. We are going to provide the binding key from the console. So I'm going to take whatever is in argv1 or whatever it's called, okay? And then I'm going to bind, actually we're going to print it out as well, so print binding q to binding key. And then we're going to do the q bind, q name, test is direct. So for better readability because of crappy resolution, let's do it like this. And the last parameter is binding key. Okay. Q name, worker, false, true, false, false, handler, and a loop. Okay. So these are all the changes required on the consumer. Has everyone caught this far up? So let me write this. So this is the queue name. This is the exchange name. And this is the binding key. Everybody got the consumer? We can move to producer now? Okay. So, for producer, let's see. We need to rename the exchange to test direct exchange, right? We need to set the type to direct. The message remains as is, but we are going to fetch the routing key, so or binding key, whatever you want to call it. Binding key is argv1. Okay, and then we have the basic publish, again message, that's fine. Test direct exchange, and now comes the first curveball, and that is that we are going to provide the binding key here instead of a queue name. This is because this is now a direct exchange, and we need to tell it to use the specific binding key, and we specify the exchange, as opposed to previous examples where we wanted to use the default exchanges from the RabbitMQ, so you have to do an extra step. Everybody with me so far? Okay. Let's test this out. Stop the worker. And now we need to binding key 1. Binding QAMQ blah blah to binding key 1. Fine, that's good. Now we're going to do same for binding key 2. Okay. Now we have both consumers or workers running. Each of them is using a separate binding key. Let's verify that. Changes queues. So we have 2 queues, One queue is bound to binding key 2. The second queue is bound to binding key 1. They're using the test direct exchange we have defined here. In connections, you can see that we have 2 connections, and we have 2 workers, and we have 2 channels. So PHP consumer, producer, binding key 1. Okay. And if I got this right, the middle column should receive the message. There we go. And now if I changed the producer to binding key 2, then the right column is going to get the message. And there you go. You now have an exchange setup and queues, and you can do your routing. Do you need the code? Let me bring back the producer code. So basically what we did is on the exchange declare, we said test direct exchange, type is direct, binding key we got from the argument value, and in the basic publish, change the exchange name and specify the binding key. Yes?
Could you bind the consumer to, say, 2 binding keys and just deliver messages through?
Wildcarding is the next topic. Step by step by step. One, two, three. Did everybody manage to get this working? Okay. Can we move forward, or do you need more time? Okay. So, I'm so happy that you guys can actually follow me, because I was scared. My first workshop ever, so don't know what to expect. Okay, so next thing we do is the topic exchange. Okay. Let's go to the simulator again. And let's see if I actually get this right from the first try. So we have a producer, that's fine. We have an exchange. We set it to topic. Okay. We have queues. Let's make them 3. Yes. It's online, GitHub /RabbitMQ simulator. This is a product by, I'm going to butcher his name, so I apologize to anybody Spanish, Videla Alvaro. This is the guy that was working with Pivotal heavily, and he is the author of PHP MQPlib and of this simulator. And basically, the current state of RabbitMQ being able to install it on your servers with ease and don't have to worry about Erlang is largely due to his and his team's contributions. So it's nice to mention him. So we have queues, and now we have come to your question. So now we're going to use the topic exchange. The biggest thing that the topic exchange allows us to do is to use words and wildcards. So we have 2 types of wildcards. One is a star or an asterisk, which will replace exactly 1 word. The second one is a hash, and it will replace 0 or more words. So let's see that in practice. So we set the binding key. fingering it all the way. Binding key, change. The second one is going to be binding key 1, change. And the third one is going to be binding key 1, or let's say 3, doesn't really matter. Let's add some consumers just for the fun, because I like to see the wheels moving. And I honestly get scared when I see the queues filling up. So, again, we send a message because this is a topic exchange, nothing happens. If we set the binding key and send it, only this one will receive it. Okay, so if I change the binding key here to binding key star, and just for the hell of it, this will do, and send a message again, only the first one will receive it. But if I send it to binding key 1, one of these days, like I said, I will never get this right on the first try. So, binding key, hash, change, send. It's one or the other. So let's see what happens if I do the binding key star. Yay. One in doubt. So we have the topic exchange, yes, edited, yes, queue. So let's get this one to listen to star.apple, for example. So if I send something, nothing goes. If I do one apple, there we go. Okay. Let's do the other one. Let's say it's some green star. Well, so green star, change. So if I do now green 1, it will go to the second one. If I do green 4, it will collect it again. And let's do something crazy now and say, okay, so we want the binding key last, binding, and do the hash. And yeah. So if I go here and do binding apple, I get it to 2 queues, because this queue here is listening to anything star apple, so one word replacement to apple, and this one here is listening to anything that is with binding, so anything after the binding keyword is a wildcard and a match for this queue. If, for example, I change, let's change this one to star green, because this will make a lot more sense. If I change the binding apple to binding green, for example, and send it, again, this queue will receive the message because it is wildcard matching, as opposed to this one, which will receive the message because it is only matching one word, and that is binding. Excuse me? You mean, okay. So you mean something like binding and then apple and oranger? Yeah. Let me think. Well, basically that would be this queue here, because it is then wildcard matching. So if we had a situation where we have one publisher sending the message with binding key binding green, and we have another publisher sending the message with binding apple. Let me do this. Right? Okay, and start sending. Basically, this one will collect anything, both the green and the apple, if you need to process them.
Okay, you can list something like these and say explicitly, I want to receive these,
Yeah, no, you can't. If I understand correctly, you're asking me if I can list several binding keys. No, one message can have one binding key. To make it clear, let's call it routing key. One message can have one routing key, so you can actually traverse the graph from producer to the exchange to the queue to the consumer.
Okay, so you can't do like a regex or
No,
anything.
no. Basically, this is the replacement because you can construct some monstrosity type binding star wish hash, and then if it matches, it will receive. So in that case, it's just wildcarding. It's not full regex support. Okay, so we have the simulation running, which is nice. Now let's do the code. Topic. So for consumer, we need to change the type of the exchange to topic. There we go. This works. For producer, things are a bit more interesting. Oh, the same. Okay. So we got everything in place, and now we're using the topic. So let's see if this works. Let's say that the consumer 2 is again listening to binding key 2, and this consumer is going to listen to binding apple, for example. 1. Yeah, let be just binding apple. Fine. So we bound them, and we do the PHP producer, and we do the binding hash. Yeah, that'll do. So we do the producer PHP, and we do the binding key 3, for example, and only the middle column should receive the message. Yep, and not the rightmost one. But if we do something like binding key 2, both the middle and the right column should receive it. And we are now basically binding the messages in the middle column to any word that comes after binding. And let's change the rightmost one to listen to anything that has binding, and then any kind of word, and then 2. So in this case, let's send it directly, binding key 2. Both the middle and the rightmost column should receive it. There we go. But if we send something like binding key, the middle one receives it. If we send something like binding key 3, only the middle one receives it. So there you go. You have now topics, and this is a good one. Maybe the best example, real-world example for this would be for logging. So you set up. Let me ask you this: how many of you here knows of Monolog? How many of you guys use it? The same thing that you would set up for the routing in the Monolog, whether you want a level to be warning or exception and stuff like that. Same principle applies here. With this wildcarding, you can set some queues. One queue would listen to any kind of information that comes from the system. The other one would listen only to the warnings. The third one would listen only to the exceptions, and you can process them separately as much as you need and the way you need it. When is the break? Damn, I'm good. This is going better than I expected. Okay, so we have this covered. Let's see. Let's do hacking. I think we can fit it before the break. So, excuse me. Hacking is basically it's a simple It's a simple thing to do. So far, we relied on server and the consumer code directly to act the message. What happened was, as soon as the message has been received by our consumer, an hacking signal has been sent to the RabbitMQ server that it has been received. In some situations and in some scenarios, this is not desirable, and this is why. For example, imagine that you want to do scrape from the HTML, some HTML on some web address, you don't care. Suppose that it is some kind of UK government site that is flaky as hell, and basically if you open two browser panes with it, it will crash it. And you send a message with an URL, and a consumer receives that message and sends out a curl request to get the HTML. And suppose that curl times out or throws any kind of an exception. Because that information is important to you and you don't want to lose it because you queue it up once a day. What you do is send an X signal to the server and tells him, okay, we received this, we processed this successfully, you're fine, just remove this from the queue. Or you can send a no-X command to the server, which means that something has went wrong and please requeue this message for later time. So you can actually control the execution flow and the amount of messages, what happens to them, whether they're going to be discarded or whether they're going to be requeued for later use. And that is, in certain scenarios like this one, that can be very, very useful. So let's put this code together quickly. So what we need to do is, let me see, consumer. Connect to a named queue now called myActQueue in the queue declare. So we have the, this is the consumer, right? Yeah. Queue declare, oh, this is going to be fun. Just a sec. So we got the handler, let's fix that. So we have the print message body, that's fine. And, okay. We have 5 more minutes to the break, so let's, okay. So we're gonna do this. Check if the content of the message is same. If message body equals hello web summer camp 16 workshop, throw an exception. THROW. And then we print the message body, or it should be, if it's not. Okay. Channel basic act. Now we're going to act the message upon successful processing. Message, delivery info, delivery tag. So each message object that you get from a RabbitMQ has a lot of metadata on it. One of them is name of one of that data point is delivery tag that is within the delivery info. And that delivery tag is basically a unique identifier for each message that tells the RabbitMQ what to do with it. So in this case, by using the basic ACK, it will allow us to acknowledge the successful reception and processing of the message to the RabbitMQ server. Okay, so we got this. Let's see what needs to. Where's my cursor? Oh, Okay. So next we need to do is declare a queue with a specific name. So queue name, myActQueue. And then we need to do the channel declare. Here we go. And we are going to do we need to exchange? Yeah. Oh, right. Okay. Declare a queue with a specific name, and then do channel queue declare, because we want a new queue. Queue name. What the hell? Oh. Then we want the queue to be, we don't want the queue to be passive, which means that don't check if the queue with the same name exists. We want the queue, we don't want the queue to be durable, which means that as soon as the last consumer and the message has been spent from the queue and the queue is empty and nothing is connected to it, it should auto-delete. We want the queue, we don't want the queue to be exclusive. Again, we had that, which means that any worker can actually access it, exclusive. And we want the queue, we don't want the queue to auto-delete. So, auto-delete. I made an error in explaining this. Durable queue means that when you are restarting the RabbitMQ server or it comes back up after a crash, the queued messages are going to survive it, which means they're going to be persisted to disk as opposed to being kept in memory. Auto-delete, and I think that's okay. That's kind of it. Then we have the topic exchange. We are going to use topic exchange, type topic, that's fine. Binding key, do we need it? Yeah. Oh, right. After the binding queue, queue name, test topic exchange, here we go. We have the binding key, and we are going to consume the message. Again, queue name, worker, false. Here we go. This one true that we had is going to be changed to false, which means no ACK. And the false means that the handler will manually acknowledge the successful reception of the message, and unless that happens, the Rabbit will consider the message not processed and put it back into the queue for another run. Okay. Does everybody have this covered so far? Do we need to see more code or catch up? Is it time for a break now, right? Okay. Oh, man. Can you hear me better in the back? I mean, I'm still going to put you to sleep, but still, you can hear me better. So how many people are missing? 2? 4? I mean, people are not here, but the machines are there, so let's give them a minute or two. So for the guys who are here, there is one important thing that I forgot to mention. For the purposes of this exercise, all of these queues are non-durable. okay? Which means that all of the messages that are put into the queues are going to be deleted when would be deleted and purged when the Rabbit would go down or the consumers were disconnected and stuff like that. Basically, if nothing there is there to consume after a certain amount of time, all of those messages are purged. In a normal scenario, you would declare your queues to be durable and not auto-deletable, so they would be able to survive your instance going down, your producers going offline and stuff like that, but your messages would be safe. And you would have like a reasonable amount of certainty that they are going to be able to operate. You might experience some loss of messages, which is normal depending on the type of crash and what happened, but you need to remember that distributed systems are unreliable by design, and that what we have currently is actually great. So, anybody else coming? Yeah. Yeah, there is actually a plugin for that called delayed delivery. I haven't played with it because my needs revolve around queues being processed as soon as possible. On the other hand, if that kind of plugin doesn't work for you, like I said, exchanges and queues are really cheap and you should not think about creating them more. You can actually create separate queues. For example, if you need a message to be processed on an hour, every 6 hours, every 12 hours or so, those could be separate queues, and you could have cron jobs that are triggering the consumers to process them if they need to be. So you can actually have the benefit if you scale things up and there are more messages to be processed every X amount of time. You can have separate queues for them and you can process them in batches. Okay. Let's see, where were we? I think we wrapped up the producer. So let's see the changes for consumer, sorry. So let's see the changes needed for the producer and the hacking. The exchange is direct and topic. We create a message, that's fine. We have a binding or routing key, whatever you want to call it. And we need to change it here to test direct. Oh, sorry, that's wrong. Test topic. This is what needs to be changed. And this as well. So we now have test topic and we have both. Okay, I think that's it. So we are now going to run one of our consumers. Building bind key one. Okay. And we are now going to run our producer with the same key. And if things go well, then the consumer is going to throw an exception. Well, now, this is awesome. What did I do wrong? Cheat again. This is the hacking, right? Yep. Consumer. Fix the path. Save. Producer. Fix the path as well. Save. Okay. Queues. So my act queue actually got created, which is good. And let's run the consumer again. Okay. And we build this. Awesome. We got an exception, which is great. Why is this great? Because as you can see in consumer, we have a check that throws an exception if the body is what we expected, which means that the message will not get manually acknowledged to the RabbitMQ server. And when we look into the management console, we see that one message is ready to be processed, which is exactly what we wanted. So to recap, publisher sent the message to the queue. Consumer got the message, something went wrong, and it was not explicitly acknowledged, so the message was then put back into the queue for later processing. Let's modify the consumer. Here we go. Modify the consumer and comment out the exception throwing code. And when we run the consumer again, here we go. Hello Web Summer Camp 16 workshop. So the message was received. And as you can see, the message was act, and RabbitMQ basically removed it from the queue. If you go here, you can see the spike. And this is, as you can see, the color code is acknowledged. So in RabbitMQ admin, you can actually monitor the acknowledge rates and redeliver rates and stuff like that. Okay. What's next? Oh, right. Next is, yeah?
The message is not able to be processed with a queue broker or whatever, stand off a bit. Will it re-deliver the message right away or try?
You're thinking about it the wrong way. The message broker does not push messages. The consumer asks for messages. So the message broker will just put the message back into the queue and wait for a consumer to ask for next available message.
Okay, so let's say we have a situation in which the consumer is doing HTTP request.
Okay.
And the network is down.
Okay.
So he's trying to do the request, network is down, throws an error.
Okay.
The message is back in the, it's not spent, so he asks for the next one, because he's a stupid consumer, he doesn't know he threw an exception.
Yeah, now I understand what you're saying. The message should be queued to the back of the queue.
Okay.
So yes, it is possible to have an edge case where you have one message that is going to crap out repeatedly, and then it's going to be re-queued, and the same consumer is going to get it, and yada, yada, yada. It's possible to have that, but that is an edge case, and that is something that you are going to handle by yourself by introducing, let's say, into a payload a variable with a number of retries, and if you go over, like, say, 3 times, you say, okay, like, drop the message. That's one possibility. The other possibility that we are going to cover later in about RPC, TDO, in about 2 modules, is to use something called DLX. DLX is basically the letter exchange, which means that if you have a message that is that has not been processed for some reason, you can actually send a parameter back to RabbitMQ that says, hey, this is something wrong with this, put it to a side. And it can go into a separate queue that can then wait for your inspection or whatever your process is to see what was wrong with that.
So I'm not able to, as throwing the exception, say, retry in 5 minutes?
No. That, I mean, you can do that, but that is on your code's end, okay? The RabbitMQ has no concept of time like that, because you need to control your consumers asking the RabbitMQ server for messages. He just holds them and routes them. He doesn't care about anything else. Okay, so we had this. We managed to get the message back, right? We saw this. Okay, so we now can move to RPC. Okay. So RPC is basically remote procedure call. What that does is allow you to execute context switching, sorry. It allows you to execute excuse me. What it allows you is to execute message from consumer or from publisher to another queue and get and wait for the response to process it further. So let's see how that actually works. So first we need to modify the producer. Okay. Test topic, that's fine. Message to be published, that's fine. Routing key is okay. What? Apologies. Oh, I'm looking at the wrong one. Sorry. So, this topic exchange. First thing to do is actually create a correlation ID. It is a unique request response pair identifier. Basically, it is your way of telling the RabbitMQ that the message should be returned to that correlation ID. And you're going to see what it actually does in a minute. So correlation ID, unique request response pair. So we're gonna set it to micro time, Jesus, and plus process ID. Get my PID. And that is going to be our correlation ID for each of the producers. Sorry. And now things are going to get a bit tricky. Our producer is actually going to be our listener as well. So listen to a temporary response queue. Imaginatively named queue. So channel, declare queue. We don't care about the name. So we went over this false, false, true, true. Okay. Callback queue is whatever the declaration brings us back. And then we do the channel basic consume. So callback queue. We don't care about the consumer tag exactly. Then we have the no local. Then we have the no ACK. Then we don't care about exclusive. And then we don't want to wait. We have no wait. And then we do a callable function, or whatever it's called. Function AMQP message. Message. Use. We pass the correlation ID. Oh, sorry. Okay. And then we say if message get. So whatever correlation ID is returned from the server is equal to what we have. Okay, and let's see if we need anything else. We don't. Okay, that's fine. So now we need to add some metadata to our message. We need a semicolon here. So add metadata. We do that by declaring an array, which will have a correlation ID key with the value of our correlation ID. And we are going to say that we want the reply queue, play queue, to have the value of callback queue defined above. So our correlation ID, set the callback queue. Cool. Okay. And now what we need to do is pass the metadata as a second parameter to the message object. Let's make it a little more readable. Okay, and let's see what else we need. Basic publish, test topic exchange, routing key, and we need to wait for the response. Okay, so this is our producer. Has everybody got that? Now we need to modify the consumer. So we need to remove the exception stuff in the exceptions handling in the handler. So we need to remove that. Print message body PHP URL. Let's simulate some hard work. By sleeping for 3 seconds. Okay. Now, copy the request, correlation ID. Well, Ubuntu. Into the response, message metadata. By again declaring the metadata array, and in it we are going to have our correlation ID. Correlation ID, good. And message get. Okay. So now we create a response message. Nitpicker's corner, I'm shifting styles from snake case to camel case, so don't hold it against me. Why hello back. And we pass the metadata as well. Okay, so now we have the response message. And now we need to publish that message. Basic publish. Response message, and I think we don't care about the name. Yeah, and we need message get. Oh, right. Reply to queue. Let's make this a little bit more readable. So we do the basic publish. We send our message. Response message. We don't care about our worker ID or consumer tag. It can be whatever. But what we do care about is the queue or binding key to reply to. And after it's all said and done, we actually acknowledge the message to the RabbitMQ. As far as queue declared, that remains the same. The topic is the same. The binding key remains the same. Worker remains the same, I think. And that's about it. So, did everybody get to this part?
Could you scroll back up, please?
Sure. Consumer or producer?
Consumer.
Roger.
Metadata. Correlation ID.
Here, wait, sorry. Here we go.
Not brackets. You get.
Yeah. Oh, come on, it could have been a cool error. Thank you. Okay. So we run the consumer. We run the producer with binding key 1, so it's the same as the consumer. It got the message, simulates it, and craps out. Yay! Internal. Where and why? Fatal error, uncaught out of bounds exception with no reply to property invar. Well, those who can do, those who can't cheat. Again, RabbitMQ, RPC, consumer. Fix the path. Kill it. Producer. So again, running the, yeah. I have an error. Let's see what I made a boo-boo of. Hello, fatal error, uncaught exception out of bounds. No reply to property. Do I actually define it? Because that would be nasty. Callback queue, correlation ID, reply _2. And what do I call here? What did I get wrong? Okay. Let's do some old school debugging. Producer binding key 1. So correlation ID is here, reply to is here. I have two messages in the queue, that's fine. Mic'd queue, 3 of them. Let me get one and see what we have. Okay, so this one is not working. So don't requeue it. Again, correlation ID, no. Now we do it. Okay, so what happened was, for some reason, the published messages did not have a proper reply to property set. So what this means is that, if I run it now, first message, second message, here we go, and response by hello back. And this is one of the common pitfalls of working with Rabbit, because you have to make sure that the payload and the message that you send are absolutely what you expect it to be. And by far, this is going to take some of like 50% of your debugging time, just running around and trying to figure out what the hell happened. Your first guess and first port of call in most of the cases should be like publish the message to the queue and inspect the message with this. Or even better, when you write your own wrapper or whatever library you use, add a bit of code that, with the debug mode, that will basically war dump the whole payload. So you can actually inspect it and see that everything is there that you expect it to be. So the consumer is still working, so I'm going to repeat it just to prove that this is not a fluke. I published the message, the consumer received it, sleeps for 3 seconds, and says response was why hello back, and the message was acknowledged successfully. And we can see it here that everything has passed properly. Has everyone managed to get this working and running? One is damn, we need to haul ass. Okay, so this is basically the RPC. Let's put this in a real-world example. Let's assume that you have to process some information, and processing of a certain piece of code requires a lot of calculation and heavy computational power. And if you do it on the instance that is currently doing it, your execution time, because it is a feeble one, will be, let's say, 50 minutes. And if you are able to do an RPC call to a beefy instance that can do it in 5 seconds and return you the data, there you go. Even better real-world example for an RPC call would be a CAPTCHA solver. So what you do is you scrape a URL, you get a CAPTCHA response, you get the image tag with a CAPTCHA, you send that off as an RPC call to a specialized instance service, whatever. It solves the CAPTCHA, brings you back the results, which you then enter into a form and move along. So this is so these are like 2 real-world examples that are really good, for RPC. So we did the RPC. Next is a time to live. Okay. There are not going to be any changes in the consumer for the time to live. So what is a time to live? Time to live is basically a way for you to tell RabbitMQ how long it should tolerate any messages in the queue. It can be per message, per queue, and per queue messages. So the distinction is quite subtle. And we're going to see. So first thing that we're going to look is per message time to live. What we are going to do is add metadata tag expiration with a length of 30 seconds. So people like me who are not fast on the keyboard can actually switch to Rabbit Management Console and actually see the message being purged after 30 seconds. So in order to do that, we need a producer, and we need to strip back and simplify a lot of things. So we need to, do we need an exchange? Let me just check. Not really. Awesome. So we're going to rely on the default exchanges that we already have in the Rabbit. So first thing to do is channel queue declare, and we are going to call it test queue. Oh, let's make it a better name, test TTL queue. Okay, nice. So next thing is we add a metadata, again a proper simple array, expiration with a value of 30,000. This is because TTL is expressed in milliseconds, so a value of 30,000 is equal to 30 seconds. Okay. We have a message, we have the metadata added. Do we care about the routing anymore? Hell no. We need to basic publish message. What? Oh, message. We don't care anymore about the exchange, neither about the routing key, so we can remove that. And we don't need to wait anymore for the response, so no loop there. Okay, and when we now run the PHP producer and switch to queues, we see that we have a awesome, and we see that we have a TTL queue declared, but there is nothing in it because I made a mess. Let's see if I can fix it. Test queue message. Oh, right. Test TTL queue. Yep, here we go. So we got a message here, and in some 20-30 seconds it's just going to go away. So we're going to wait some more. And there we go. It expired, and RabbitMQ basically removed it. So, okay, let's go to per queue TTL. So first thing we need to do is change things. Metadata now cannot be a simple array anymore. It needs to be a MQP table object. Oh no. Use PHP MQP lib wire and then MQP table. There we go. So MQP table. Nope. Oh, come on. So it's an object that, guess what, takes an array. Ain't it beautiful? And the tag that we want to have is expires. And again, the value is in milliseconds. So I'm going to set it to 20,000. 20,000, 20,000. Okay. And then this is the message. We need to queue declare. Channel. Was this deleted? No, it wasn't. Okay. So we're gonna queue declare. And the queue is going to be named test expiring queue. Well, okay. Again, bulls, false, false, false. We got 1, 2, 3, 4, 5. and then we need to have the metadata. And there we go. 1, 2, 3, 4, 5. Okay. So after that, we have our message that at this point doesn't have the metadata because it is on a queue level. Message, we don't care about the worker ID and consumer tag, but we care about expiring. There we go. Okay. So did everybody get this part? Okay. Let's see if I made a mistake. So, producer, queues, expiring queue, it has one message in it, or we can do like whatever, 2, 3, let's see what happens. And we wait. And gone. So the queue was alive for 20 seconds or so from the reception of the last message, and after that it auto-deleted. So again, if you need to do some temporary processing that does not require the queue and the message to survive longer than what you need, you can use the queue-based ETL, and it will auto-delete and clean up after itself after a while. And the last one is per message queue. Let me see. So what do we have? The metadata is going to be, instead of x expires, it's going to be x message TTL. Did I read this right? No. Dashes, no. Okay. And we're going to leave it at 20 seconds, which is fine. Channel declare TTL queue. Okay. And we are going to be using the same thing here, right? Oh, no, sorry. Excuse me. There's a message, there's a metadata, there is queue declare. Okay. TestTL queue 1, 2, 3, 4, 5 false, and pass the metadata. Fine. We have the message as well, and then at the end we need to correct this. Okay. So, boom. Yeah, because the queue exists. Let's purge the queue. Okay, cheat time. TTL. What do you do? Per queue message. Oh, right. Fix the path. What? Again. Yeah. TTL queue. Purge it. Right. Okay. So we have the time to live queue that is going to take like, what did we set, 20 seconds, and after that it's going to like purge all the messages in the queue while keeping the queue. And there we go. And this is again good if you need to purge all the messages after a certain time, so you must ensure that no stale message is there. So if you have some kind of information that is time sensitive and that is invalid after a certain amount of time, this is the best way to ensure that everything will be purged, regardless of how much it was processed. Then, okay, so now we come to the DLX. Okay. So DLX is basically a dead letter exchange. What that means is that if your messages are not being processed or act, they can be put aside for later inspection or separate processing. I think we discussed it with somebody over the break. How you can do that? You can either set the TTL, so if the message expires, instead of it being deleted, it will be sent to a separate dead letter exchange queue, or you can actually do the when you send the not explicit not acknowledged command to the RabbitMQ server, you have a requeue option. You set it to false, and then the message, instead of being dropped, it is going to be sent to the dead letter exchange. Again, dead letter exchange can be, shouldn't be application-wide. It should be queue specific. So if you need to have multiple queues with the dead letter exchanges, my suggestion is that each of them has a separate one, so you can actually inspect all of these messages and process them afterwards, or inspect them separately, so you don't have a situation where the messages get mixed. And this is a mistake that cost me a lot at one point. Let's see now. So for the what do we say? DLX, yeah. We are going to use the per message queue as base. We are going to add a dead letter exchange metadata with a test DLX exchange value, and we are going to change the name of the queue to test DLX queue. And that is going to be in producer. So this, I'm going to cheat now because we are getting short on time, and I would really like to get to tell you about this last part of the talk. So we're gonna speed through things here just a bit. And consumer. So you have a directory called 00x DLX, 008 DLX, where you can copy and paste. And this is what we need to do now. If I run this, I need to run the consumer first, if I remember correctly. So PHP. Yep. Fix the consumer path as well. Okay, so let's check out the queues. As you can see, there is a AMQ again, some kind of like queue that is going to be processed in some way. And if I run the producer again, what we have is a DLX queue. It has been declared, and here it is. And now I need to run the consumer to connect it. And the consumer is going to generate some kind of temporary queue. And after a certain time, the DLX message is going to expire, and it's going to be moved to that temporary queue, and the consumer is going to pick it up and process it. There we go. And it disappeared, right? And as you can see on the bottom, hello summer webcam, the consumer actually received the message as a DLX and processed it. The last thing that, the second to last thing actually is that we are going to talk about is priority. So by default, all messages in the queues have same priority value. We can change that to be different, to have some messages to have higher priorities, but depending on other factors, the results might not be what we expect. So let's plow through this. priority 009 directory. This is the consumer. I'm going to fix the path again. Producer. Fix the path. Okay. So here we go. We are going to declare, so on line 11, we are going to declare a new exchange called test priority exchange. It is going to be a direct exchange. We are going to publish 3 messages into the queue. They should be processed in a 3-2-1 order because we are going to give them priority and the higher number should win. We have standard message that we have here. So data WebSummerCamp16 added the identifier for the priority, so we know what's going on, and we have the metadata that is being sent. We are going to do, just for the fun of it, we are going to do basic batch basic publish, which means well, for the lack of the better explanation, think transactions in terms of message brokers. So all of the messages are going to be put in a single transaction and pushed off to our RabbitMQ as a single call, basically batch processing them. And on the consumer side, again, we are going to act the message and we need the explicit queue name that sets the priority, direct queue bind. Oh, okay. We're going to disable this. So everything else is mostly standard. So we have one consumer running. Let's have the other consumer running. And now let's publish the messages. Is this the expected result? Really? Yeah. So let's do it again. 1, 3, and then 2. So we have a problem here because the messages are not being processed in sequence. If you have one consumer and we publish the messages twice, again we have a problem. They're going to be sorted as they should be. If on the other hand we turned on something called QoS, which is basically next thing to talk about, things are going to be better. Oh, actually it's the same. Sorry, I got this one whole way backwards. Right. So the messages are actually being processed in the order that they should. So what is next? Oh, QoS. Okay, so what we just seen here, and I'm certain that like most of you missed it because I didn't make a note of it, is the way RabbitMQ actually assigns messages. It basically does a round robin. So what it means is that it is actually looking for the first available consumer to pass the next message to. Sometimes that yields strange side effects in the manner of if you have like multiple workers, let's say 3 of them, one is going to be utilized 100% and the other 2 are just going to sit there. If you use something like spot instances on Amazon and you're charged by the hour of use, that's basically waste money. What you can do, excuse me, what you actually can do is use something called QoS. It's quality of service or whatever it's called, which you can then tell RabbitMQ for each of the consumer reserve a certain amount of messages. That means that the messages are going to go from the ready queue to the prefetch, and then they are going to be processed. The thing to note is when we were talking about the when we were talking about the RabbitMQ plugin here, the distinction between delete and purge. If you have messages in Prefetch by using QoS, those messages will not be removed from the queue because they are determined to be delivered to a consumer. Only when consumer gets disconnected from the RabbitMQ by going down, by exiting, whatever, then those messages are going to be put back into the ready queue, and then they can be purged. So let's take a look at the example for that. Again, I'm going to plow through this. QoS, consumer. So what we do is we have a QoS exchange. It is a direct type. We explicitly set the queue name to test QoS queue. We define a binding queue, QoS. We define the worker ID to be worker ID plus process ID. We declare the exchange. We declare the queue. Again, nothing new here. We bind the queue to the exchange. So let me just put this so people will see better. We have the handler. Again, message body. Show it. Let's do the sleep. We acknowledge the message, and then we have a basic consumer. Again, basic consume the messages and the loop wait. We are currently going to disable the QoS because I want to demonstrate first what it looks like without QoS and with QoS. Let's do the producer. Again, declare the exchange, queue name. Basically, this part is identical to the consumer. Let me just see. And we are going to do some fun things here. We're going to generate 30,000 messages and put them into a queue. And we are going to, and then we are going to let the consumer process them. So, did I fix the yes on our consumer as well? Yes. Okay. We are going to restart the consumer, and I'm going to push in. So because I'm basically using sleep, the messages, as you can see, are being processed in a different speed. One will be favored, the other one won't. On two of these, you might not see the difference, but let's see if we can do the third one as well. And as you can see, this one is not being used at all because there is enough resources in first two consumers to utilize all of the messages that are in queue, and this consumer just hangs waiting money, or just losing you money. Okay? Everybody with me so far? Okay. So what we can do is enable the QoS. In this case, we are going to ensure that there is 5 messages per consumer prefetched, which means the RabbitMQ server is going to do a round robin and just serve 5 messages in a pre-queue that are going to be ready and available to each consumer, so they can be exploited equally. Let's, for the fun of it, make sure that we are going to do it on an empty queue. Purge. Okay. So run the consumers. So all of them have the same starting position. And I'm going to run the producer now. And now they are basically being utilized. And because we have all three of the workers are being utilized, and because we have a sleep function, basically random sleep here, they are doing different kinds of sleep. So we are simulating the real world conditions of some workers being faster, some being slower. But the point is that all 3 of them are going to be treated equally and supplied equally with the same amount of messages to the best of RabbitMQ's abilities.
So if a worker goes down, the messages that he prefetched
Are put back in the queue and redistributed to the other ones. The downside of this is if you put a large enough pre-queue fetch, a large enough QS, so a large enough prefetch, let's say 500 messages, and then when you get to the lower numbers where you don't have enough prefetch messages for everybody, then the consumer that was fastest first to consume all of its prefetch queue is going to get whatever is left. And that sometimes might not be the desirable result. So you might end up with 2 or 3 or maybe 4 consumers just idling, which is not that big of a problem, but your consumer that is actually working might get slower because these are like certain messages, slow HTTP response or something, and things are going to wait. So this is the QoS. Let's see what's next. QoS, priority, oh, right, API. Okay, this is going to be fast. So, on your RabbitMQ console, you have an API. Yay! You access it by adding localhost port 15672/API, and you can actually see what's going on. You have examples, you can curl, and you have a nice reference for each of the API endpoints, what they expect, like get, put, delete, post, and stuff like that. Also, you can see the examples of the payload that they are going to, that they can take and things you can do with that. So let's see what we can do. README. Okay. So let's get an overview of things that are, excuse me, BXS. Let's make some screen space. So you want to, all right, I can't paste. So we do the curl guest. The endpoint is localhost API overview, and when we run it, we get back a nice JSON payload that we can parse and get some information from it. Let's create an exchange, and I should warn you that by itself this won't work. Oh, yikes. I need to create a scratch file. No. Again. Excuse me. Oh, come on. How do you create a scratch file on Linux? Tools. That's what they need. Tools. Wow. Okay. I need it because of the indent to make a nice thing. So let's paste this. Paste. So this is going to create a test HTTP exchange that is going to be type direct and it's going to be durable. So I put it, I got a nice response, and when we go to the localhost, RabbitMQ management, and we go to the queues, oh, that was an exchange, sorry. There we go, test HTTP exchange. So we can create that. Also, we can do the create exchange, we can publish messages to it, we can create queues, list it, and etc., etc., etc. All of this is available to you in your repos. Also, there is one thing that it shames me to say, but I need like a year and a half to figure out that it actually exists. If you go to RabbitMQ and instead of an API, you click on the CLI, enter the CLI, you will get to this page. There is a link here called that you can save, and it is actually a Python script which basically is a wrapper around these curls. So it allows you to have the same kind of interaction with the RabbitMQ from your console, but without like having to write god awful curl requests. So let's see how it works. I have it already in the folder. So you might actually need to do chmod a+x so to allow execution. For example, let's see the overview. So you get nicely formatted results. We can declare an exchange. We can list exchanges. So you can do all matter of stuff. Everything that you are able to do with curls, you can do with this script. But just I personally find it a lot more appealing than to writing curls back and forth. Okay, and with that, we are going back to the slides. Built-in retina. Don't mirror the displays. Okay. Where's the keynote? What? Ah, here we go. So, now I've shown you the basics of RabbitMQ and all of the bits and pieces that you actually need to do something with it. And now when you need to apply it to your own code and to your own projects, what you in essence are going to do is take an extra code and you're going to split things up. For example, if we look at the example from the beginning of the story, there is going to be one set of workers that are going to get the HTML. There is going to be another set of workers parsing it up and updating the database. Another set of workers to create a screenshot from the URL. You add as much publishers as you need, and the message broker like RabbitMQ can take it. And this is very good because you can split things up and you can scale as much as your client wallet allows, or heaven forbid, as much as your wallet allows. So now, congratulations, you're distributed. And this was quick, wasn't it? Short and sweet. Nah. This is just the beginning. First thing is your workers will exit because of timeouts, because no jobs available, some exception. Your workers need to be kept running constantly, so you have to use daemons to keep an eye on them and start them in any number of instances you need. Most popular daemons would be supervisor and upstart. Upstart is basically Canonical's take on supervisor that was integrated into Ubuntu. Both are well documented, both are straightforward to use, both have nasty limitations. Supervisor specifically has a limitation of number of instances it can run at any given time. If you try to run like more than 200, 250 or 350 instances of one worker, it will crash and it's slow as hell. Upstart, on the other hand, will handle that, but if you add multiple signals for the workers, for the Upstart to handle, like stopping and starting, some of them he might miss. I have no idea why. Then we have like running order problems because RabbitMQ is FIFO, first in, first out. Multiple orders means that there is no reliable order of execution, and again, order of execution in distributed systems should really not matter. Then we have like problems with reliability. The assumption is that a message gets executed and it will be processed sometimes, but you can't reliably know when. Another problem is that if the worker fails, a job will fail, and the issuing server will move along, and while you think that there is 5 messages in the queue, in reality one only passed and things don't work anymore. So if we talk about the example from the start, if you're uploading an S3 and HTTP request, if the request fails from within a worker, you should requeue that message for later processing and make sure that the failed message gets called again sometimes. Like I said, you need to realize that distributed systems are unreliable by design, but that is what allows them to scale. Even with the fact that there are different ways of ensuring reliability, this is still a problem. Then you're gonna encounter data problems. So imagine you have a setup web server that publishes things to RabbitMQ. We have consumers, and we have that get some data and then process it and push it to the DB servers. What happens if the DB servers fail? Well, obviously, everything will fail because this is a single point of failure for the system, and that tends to happen quite a lot. So what can you do about it? In distributed systems, the location of the data is very, very important. And actually distributing the data to different locations tends to solve that problem. The wrong way to approach working with messages would be just to give, for example, an ID in the message. And then when the consumer gets the message, he needs to actually go to the database and look up all the pertinent information and then to process. Because then you're in a situation where worker not only needs the database to write things, but it also needs to read from it to work. The proper way to handle this is to provide all the relevant information to a consumer in a payload so it can do its job and resubmit for later execution if the database server is not available. Another option is that if you have like multiple servers that care about different problems, you can split the database with sharding, for example, and your data can be co-located at those specific workers and locations. You might also have to denormalize the data because by storing duplicates of data, it will allow you to do very fast operations because you avoid having joins, and because the data is normalized, it is available in different tables, and you have very, very cheap operations. Because then you can actually ship different subsets of data to different processes that deal with them and not having to access anything else. Then you're going to encounter this lovely thing. It's called the CAP theorem. So we have consistency, availability, and partition tolerance. Consistency means that data is consistent across all of the nodes. So you have 100 servers, they should all have the same data. Availability means that if you issue a request, you should know if it's failed or not. Partition tolerance means that if one of your nodes goes down, then the system will still work. And here's the fun part. You can have only 2 of them. There is no system that can always be available, withstand a node going down, and give a response if the read-write has failed or not, DB systems especially. What you need to realize is that in most cases, consistency is not important, okay? Because once you eliminate consistency, you can have partition tolerance, which means if one of your nodes goes down, the system still works because data is stored somewhere. And then you can have availability because if at the time of node going down, you try to write something, you don't actually care if it succeeds or not because it is going to be requeued for later execution. What that means is that you have something called eventual consistency. What that means is that eventually all of the data will be same across all of the nodes, but it might not happen right now. Most projects can support that unless you're dealing with some high priority changes, like user logging and changing his password. This actually needs to be available immediately across all of the nodes and should be handled directly. Opposed to that, if you're logging something like user clicks, that does not have to be immediately available across the nodes. A node can go down, when it comes back, it will update the database, and eventually clicks will be tallied and displayed. The next thing you're going to encounter is race conditions. So imagine if you have like 100 workers and they do different things and update different items in the database. How do you handle a situation where you have to make sure that one worker does not override or undo what another has already done? Situations like this are called race conditions, where two or more processes are trying to update the same things at the same time, and depending on basically luck or random factor, one of them will succeed and one of them will fail. The way to solve that is to use something called atomic operations. Atomic operation is a concept where you want to update, insert, or delete data, but it has to happen in one click. In CPU terms, it means one cycle, but in most cases, it means nothing else can happen between when that process is running. An example of the atomic operation would be logging the number of views on a video, because you just want to increase the counter, but not by first reading the value, then adding it and saving it. You just want to issue a +1, and database should happen that. So if you have a lot of processes changing the same records at the same time, in theory and in practice, they will never fail because you're using atomic operations. And I mean, you did things right, you tested it, staging works great, you deploy to production, and then things start to fall apart randomly. The bigger your system is, the things will fail more and more. It is not a probability, it is a certainty. Network drops, latency drops, servers fail, disks fail, all sorts of things fail, starting from PHP and segmentation fault, like the most random error you can get. If it segments out, you have no idea why it happened, you have no logs, no idea which request it was handling, you just crash with nothing. I mean, MySQL can fail, Mongo can fail, Gearman can fail, Rabbit can fail, network instances can fail, CPUs can fail, disks can fail. Things fail all the time. And that's the way it is. Basically deal with it. How do you know things are working fine? Honestly, you can't. If your script consumer or producer have a small bug, how are you going to check the logs of all your servers, even if you have manpower? I mean, it is easier, but most people don't have that kind of manpower at your disposal. In most cases, people really have no idea what's happening. And the more complex your system becomes, the more complex your network topology becomes, the more you will say, I have no freaking clue what's happening, you know? So you need to look at the ways and tools that can tell you at any kind of scale what is going on and what is actually happening. Debugging is hard because once you deploy things, you will encounter something that you can't. You will encounter things and situations that you can't simulate locally. Cluster rack in the data center has a slow network pipeline that might not be like good enough. Good luck simulating that in local conditions. Or you're working with MySQL database that does not support atomic operations, and when you need to update things and maybe log them, deadlock starts happening and you have no idea why. You need to realize that once you launch something, it has to live, because you can't debug it anymore and you cannot make changes easily, and this is not a script on like one server, you have multiples. And you have to find ways of looking at it from bigger scale and realize what is happening. The easiest way to figure out if a system is working or not is to monitor it. You can use it on any sort of scale on different parts of the application. What it involves is measuring all sorts of different parameters on the system so you can count basically everything, you know. For example, every time a consumer gets a job from the RabbitMQ servers and processes something, you increment a counter, then you graph it, and then you can see how many counters at any given time have been incremented. So all of a sudden, if there is a drop, you know that something is wrong, and you can start fixing it by looking for clues. For example, if we are talking about product processing and it is done with HTTP requests, you want to know how long a request takes and what sorts of error happens in those requests. So you graph the response time, graph the number of requests you're doing, and graph the error rates. So every time error happens, you can improve upon that. When you aggregate all of that data in one place, suddenly you see very clearly every action of the system and you know what is happening. And this is pretty much the only way to do it. When you run something locally, it might take 5 seconds, 10 seconds, but actually you have no idea what it means, because when you deploy it, then you have actually a context and it means something. One of the best tools out there for gathering this kind of data is StatsD from Etsy. It's a daemon running on a server. It allows you to collect measurements and set it. It stores them on a server so you can grab them later. When do you have enough metrics? In short, never. And I mean it. The more metrics you collect, the fuller picture you can have about the state of your system. A lot of measurements involve collecting data from all sorts of different things: memory usage, IO rates, CPU rates, etc. Eventually, once you measure your application, you know what's happening. The sad fact is that even if you log everything and count everything, those are going to lie to you. You know, they don't do it on purpose. It is just sometimes you encounter a piece of code that looks okay on the service, even after analyzing it, it works okay, but when you put it in production, all hell breaks loose. For example, one of the applications that we were developing was using DynamoDB for the backend, and we had multiple backends. So, crash course, what is DynamoDB? It's Amazon's take on document or NoSQL databases. It is built with speed and scale in mind, and by setting the proper throughput of reads and writes, you're being charged money. The more throughput you need, the more money you will spend. That being said, after 2 years of using it, I honestly believe that this is everything that is wrong with NoSQL databases, and this is coming from someone who has cursory knowledge of database systems. Back to the story. The application in question processes about 40 million items a day. 40 million items multiple times a day, so it's quite normal to have 2 or 3 runs a day. When you do the math, it means that you have like 10 millions of new records per day. The data is stored in temporal tables because Amazon, and that means that for every day you have a different table. Getting data out of them is a separate world of pain. And these are Amazon best practices. The login was in place, the metrics were here to follow the ingestion of data, to catch the exception, and we are handling them, and everything looks good. The data is being written in batches, as it is, again, optimal way to do it, using the batch writer from Amazon. The new deploy is running smooth, everything is fine, and then a message on Slack arrives like, are we writing data to the DynamoDB? And like, what the hell? I'm looking at the console for DynamoDB, the data is missing. I mean, not a bit of data, we are talking about a lot of data. Over a course of a week, over 40 million records were lost. We have no idea where they are. The logs are clean, the metrics are clean. What's going on? I mean, I'm scratching my head for multiple hours. I have no idea what's going on. I'm running the consumers manually. Everything is fine. And then I start wondering why there are no exceptions, and I mean ever. I mean, I like to think I'm good, but I'm not that good, honestly. And that leads me to the docs, and this is basically the constructor for the client. And as you can see, it basically takes an array, and array has a metric crapload of options of different kinds. And unless you're a careful leader, you're going to miss it very easily, because at Amazon, apparently nobody knows how to bold text. There is a key called error there, to which you can pass a callable that will be called in case of an error, and you will get an exception of what happened. So fine. So let me say this again, what is happening. By default and by design, when an error happens, batch writer will ignore it, drop the payload, and continue giving you a false positive, which in turn will cause like 4 days of data being lost. On the other hand, if you register a callable, when you get an exception, the argument doesn't tell you much. And by the time you get an exception, the payload has already been dropped, and you're left there like twiddling your thumbs and thinking happy thoughts. So now I have an error handler in place, and I can see what's happening. And now I'm starting to lose my mind, because the problem is that 60% of the cases boil down to one thing: typecasting. Dynamo data needs to have its data typed. And it only has primitive types like number, string, and stuff like that. Or I think it's text. Ultimately, the payload is in JSON. And if you do not encase your numeric values, Java will try to infer types from the past value and then it will pass it into a DynamoDB, which will start screaming having a piece of it, resulting in an exception. So you need to encase your values and send them over as strings. The other 40% of the exception was that string was along the lines that you cannot mix multiple types, which would be fine unless there was a little tiny detail that I was actually using a string. So I was using a string type and putting numerical and alphanumerical data in it, and sometimes, just sometimes, DynamoDB would not like that and like scream. So I never got to the bottom of that. I mean, the failure rate was high enough. What I did is basically stop the queues, stop the consumers, because we were using Rabbit. The queues were getting filled. While the queues are getting filled, I'm rewriting the part of the application and consumers that are actually using them. I'm switching out Dynamo for MySQL. When I was done, I just started the consumers again. They picked up all of the messages and they caught up and they entered all the new data into MySQL. I was done. Then we have this. Oh, awesome. We have very little time, so I need to share this one with you because this one is like really important. So you now have like a system that is writing to the database, and it's not giving you the performance it needs, and you have no idea why. I mean, you're measuring stuff up, and you see that it's sometimes slowed down, and you don't, and then it goes back to full strength. Completely random. You don't have a pattern inside. Things are, chugging along, but you know that something is wrong under the surface. Logs are clean, metrics, the one that we have, are good. So I decide to start timing different parts of the application and processes. And suddenly, once graphed, the values show a spike, and they show that you need a lot of time to process the message completely. So now I know what to track and to measure. So I add more timers and per segment of the operation, and it turns out that the database writes were slow, and that a lot of time is passing before they are completed. So let me ask you this. If you have, let's say, 2,000 workers, and each of those workers is writing to the database, what do you call this? Can anybody tell me? Oh, come on. You know this, I'm certain. Fine. DDoS. We were basically DDoSing our own database. Lovely. And this is like an important takeaway. The moment you start working with distributed systems, you have to think laterally. You can't think linearly. I mean, you need to identify the parts of the system that are slow and that might not need to be processed immediately, and then you spin off to a separate queue, because then you can devote separate power and instances for them to be processed efficiently. So what do? In this case, again, you take an X to the system. You rework the system just a bit, so the dedicated consumers are writing into the database. Which allows you, I'll be over soon, sorry, which allows you to queue things up and then processing at full capacity, and any data that needs to be written into that database is being pushed to a separate queue. No more waiting time. The main process is even faster. On the other hand, now that you have a queue of the messages that need to go into the database, they can now be written in batches. So you can take 100 messages from a queue, put them in a batch, and put them in a database in one insert. So that's even faster. So you gain things. And because of that, we got a lot more performant, and we were around 200% more than we needed. So we could basically cut down on half of our infrastructures. So we basically saved a ton of money and stuff like that. Who was on the Ancon talk yesterday? Okay. Long story short, we had a problem. Basically, one of our instances just stopped, like froze. You log in, things are like slow as molasses. Yeah.
Just one, I want to say one sentence. When we finish, after the reception level, we will have a group work.
Yes, sir. I log into an instance, everything is slow, like nothing is working. I put on an HTOP to see if something is stuck in eating memory, nothing is, and then I do the DFH and I see that basically on a disk that has 100 gigabytes of data, I have 0 bytes free. I go into the logs and I discover that I have one log that is like 80, 90 gigabytes of size. I can't do anything about it. I delete it. I forget about it. Monitor the system a couple of days. For the next 6 months, everything is fine. Again, it happens. This time I pick the logs, take it on my machine, and I start unpacking them. I had to stop on the first run because 300 megabytes of archive yielded 50 plus gigabytes of size of log file. So I have to stop that. I pick another one. 100 megabytes, unpack it, 26 gigabytes of text, which is great. So I look at it, and 99.9% of it is basically one message. What's happening is that we are using semaphores and arrays, and under certain condition that arrays goes out of bound, and PHP just prints out the warning consistently. So it just fill the logs of 80 gigabytes of it. Again, no unit tests, no metrics in that segment of application. That's changed now, but it took 3 lines to code and add a couple of metrics, but still, this is one of the things you will encounter. Then there is, the last one. So when you work with distributed systems, the client expects you that you can scale them up quickly. Unfortunately, sometimes that is not possible. In our case, in case of one of our systems, the problem was the technical decision that files that needs to be processed are stored locally. That worked fine until more data was needed to be processed. So we basically killed the server again because we didn't have enough file nodes and enough CPU power to handle it. So the client says okay, sure, let's spin up more instances, and I was the one that had to tell them that we can't. That was a lovely talk. The thing is that problem was the local storage of files, and if you need to scale up on multiple instances, and you start talking about distributed systems and stuff like that, you cannot use the word local, so you cannot have local storage. What you need to do is create a network storage, so all of your instances can actually access all of the resources that you need and process them quickly and efficiently. That took 3 days to change, but still it was slow. I again put more metrics on it, try to figure out what's going on, because all the files now are on S3. I mean, I can put 5 times more power on it and I'm still getting low results. What's going on is that I'm basically trashing the disk. What happens is we're using WK-HTML to image. So I'm downloading the file from the S3, storing it in a temp folder, calling the WK-HTML, which is processing it, putting the file back on the temp folder, and then I'm uploading it to this S3, which is grossly deficient. So I did a little digging, and the version that we're using does not support streams, but it turns out that the version that was released a month ago or so has support for streams, but it is undocumented. I changed that. And suddenly we are again performant, 50 or more % over what we need, which is great. And again, system worked beautifully, it caught up, and everything was good. So what I want to say is, when you're dealing with distributed systems, you're going to encounter a lot of weird things. This is the closest you're going to get at programming a living being, because the distributed system of any kind is going to respond differently and have completely random responses depending a lot on external factors. And if I have to describe the whole experience of working with distributed systems in one image, it would be this. Things are burning, you're sitting, this is fine, I'm good. Thank you.